Okay, let's go over the practice test here. I try to give like sample problems of about most of the kind of problems that you're likely to see, so that you can get good at doing them. Within the regular test course, then you should be able to do these things. Okay, so the first one is just using Newton's law, universal law of gravitation, this one right here. So it's pretty much a calculator problem, which does not make it easy. M1, M2 divided by distance squared. One thing we got to be careful of is units. Everything should be in kilograms and meters, and then we can use the normal G. And it looks like I did give them to you in all the right units, so you just got to plug in the numbers. So it's 6.67 times 10 to the minus 11th, and then we have 50 times 700 on the top, and 19 squared on the bottom. And don't forget to square that. Here the only scientific notation we have is this one, so I'm just going to do all the numbers as normal and then multiply by 10 to the negative 11th at the end. So I go 6.67 times 50 times 700 divided by 19 divided by 19 again, and I get that is 646.6, let's say 647. 647 times 10 to the minus 11. Again, I just did all the numbers and then just kept the 10 to the minus 11. The way to write scientific notation is one number point all the other numbers. So this really, we shouldn't leave it this way. So this should be written 6.47. Since we made this number 2 smaller, we can make this 2 bigger, or multiply this by 100, which makes it 10 to the minus 9. So times 10 to the minus 9. Again, we take the 100 out of here, take the 2 decimal places out of here, add them onto here, so it makes it 2 bigger, which means less negative. And our units are newtons because we kept everything in the right units, kilograms, meters, so our force will be in newtons. Obviously a tiny force. You don't stick to a horse like magnets because gravity is weak. You stick to the earth because the earth is big. The horse isn't big enough to attract you very strong. Okay, so let's look at number 2 here. So you go to a planet. The 1.2 kilogram mass of spring scale weighs 18 newtons. What is the mass of the planet? Okay, so if you know little g and you know the size of the planet, you can figure out its mass. That's the idea here. So let's figure out little g. So we know that the weight is mg, which is, we said the weight is 18 newtons. And that's equal to m is 1.2 kilograms, so times g. So little g on this planet is 18 divided by 1.2, 18 divided by 1.2, so 18 divided by 1.2 is 15. So it's 15 meters per second squared. That's what g is on this planet. Okay, now we know, and I'm just going to derive it, even though I have the formula up there, we know that the weight, mg, is the force of gravity, which is big G, mass of the object, mass of the planet, divided by the radius of the planet squared if you're standing on its surface. Those things cancel out. So now we can solve for the m here. So put the r squared on the top on the other side and the g on the bottom. So the mass is, see, g on the top, r squared on the top, big G on the bottom. Right, if it's in the top over here, it's in the bottom over here. It's in the bottom over here, it's in the top over here. And now we plug in the numbers, being very careful. So g we just found is 15. The radius is, okay, I put it in meters, so we don't have to worry about changing it. So it's 4.1 times 10 to the 6 squared. And then g we know is 6.67 times 10 to the negative 11th. Okay. Again, I'm going to do all the numbers separately from the sign notation. So this is 15 times 4.1 times 4.1 again, times 4.1 times 4.1, divided by 6.67, and I get 37.8. So that's 37.8. On the top, we have 10 to the 6 squared. That's 10 to the 12th, right? 10 to the 6 times 10 to the 6 is 12 tens. So we have 10 to the 12th on the top. We have 10 to the minus 11 on the bottom. It's always the top number minus the bottom number. 12 minus negative 11 is 12 plus 11. So that's 10 to the 23rd. So it's times 10 to the 23rd, which we assume it should be a big number. The Earth is like 10 to the 24th, so that makes sense. And actually this is 10 to the 24th because it's always, again, we should change this to one number, 3.78. Since we made this one smaller, we got to make that one bigger. So we add 1 to it, so it's 10 to the 24th. And our units are all the right units, newtons and meters and everything, so we know this is kilograms. So our mass of this planet is 3.78 to the 24th kilograms. So it's pretty cool. All you gotta do is bring a spring scale and a mass to a planet you land on and weigh it, and then you'll know G, and if you know how big the planet is, as you're flying up to it, you measured how big it was, you can figure out how heavy it is. Pretty cool. Okay, this one here, the orbital formula, you should know where it comes from. I have it up here, right? That's why, and this square root, just the way that, it's all the way over, that's what it means. Square root of everything there. So, like here means square root of 2, just the symbol and this in word doesn't go all the way over. Okay, so the orbital velocity. So for the orbital velocity, what that means is the centripetal force is supplied by gravity. So we know the centripetal force. If you have an object like the Earth going around the sun, so we have the centripetal force on the Earth, which is mv squared over the radius of the orbit, how far you are from the center of whatever it is you're going around. That's supplied by gravity, which is big G mass times the mass of the big thing, the thing you're going around. Here's you, this is the thing you're orbiting around, divided by that radius squared. We want to solve for V here. So again, centripetal force going in a circle around something, how fast you got to go, how fast can you go with gravity supplying the centripetal force. Okay, so your mass doesn't matter. Same mass, it could be super heavy, super light, you're going to be going the same speed at the same distance when you orbit. Put the r over here, that cancels out the squared, and then take the square root. So right away we can just write down that V is the square root. We have a big G and a big M in the top and one R left in the bottom. So big G, big M in the top, R in the bottom. The point of this is we know that this formula simply comes from the centripetal force is being supplied by gravity, which is amazing, right? That you can just derive it that simply. And of course that's what Isaac Newton did. This is for a circle. All the planets go in practically circles. They're really close, so these work really well. If you want to go in a more elliptical orbit, you can go faster. And so the faster you go than this, the more elliptical your orbit becomes until you go the escape velocity, which is the square root of 2 times this, and then you're gone. So you can't go too fast in orbit or else you escape, and that's the square root of 2 times this, as I wrote up here. Escape velocity is root 2 times the orbital velocity. Alright, that's number 4, Mercury. That's the real mass of Mercury. That's what its radius is. So what is G on Mercury? Well, we just use the formula that we just came up with over here. Little g is this formula right here. Little g is big G, m over r squared. So little g is big G times m divided by the radius squared. And then you just plug the numbers and you're really careful. 6.67 times 10 to the negative 11. I put it in kilograms, so I'm not trying to fool you. 3.3 times 10 to the 23rd kilograms divided by 2.4 times 10 to the 6 meters. Oftentimes this one's given in kilometers because that's what you deal with big numbers. Make sure you change it to meters if it is. Add 3 up here in the scientific notation. In this case, we don't have to. Okay, so again, I'm going to do the numbers and the scientific notation separately. So I go 6.67 times 3.3 divided by 2.4 twice. So divided by 2.4, divided by 2.4 again. And my number is 3.82, which I don't have to change because it's one number point to all the other significant numbers. And now times 10 to the what? So on the top I have 10 to the negative 11 and 10 to the 23. So 23 minus 11, they add up to 12. So I have 10 to the 12th on the top. On the bottom, I have 10 to the 6 squared, which is 10 to the 6 and the 6, which is also 10 to the 12th. So they cancel out, so I don't have to worry about it. So it's just 3.82. So I can erase my times there. And so the acceleration of gravity is 3.82 meters per second squared, which is pretty reasonable, right? On Earth it's 9.8. On Mercury it's 3.82. So you weigh about, a little more than a third as much on Mercury. You're going to be a lot lighter and stronger on Mercury. And that's how you figure it out. Okay, how fast a satellite would have to go to orbit Mercury just above its surface? So if you threw a rock on Mercury, which has no air, so you could, and if you're on the tallest mountain on Mercury or something, how fast would you have to go to make a nice circular orbit, the barest minimum? So that's just our orbital velocity. That's this formula here. So again, just plugging in big numbers, square root of gm over r. It's very similar to this, right? This g is big gm over r squared. And here it's gm over just 1r, and it's a square root. So it is different. But okay, so square root of 6.67 times 10 to the minus 11 times the mass of Mercury is 3.3 times 10 to the 23rd divided by the radius, 2.4 times 10 to the 6. What I'm going to do again is the math inside, and then we can take the square root. So 6.67 times 3.3 divided by 2.4 is 9.17. So that's a square root of 9.17 times 10 to the minus 11 plus that is again 12. 23 minus 11 is 12. Minus 6, we have a 6 in the bottom, so times 10 to the 6th. So it's the square root of that. Okay, square root of 10 to the 6th. We can do this. Square root of 10 to the 6th means 10 to the 6th to the 1/2 power. You multiply exponents. When you raise a power to power, you multiply 1/2 times 6 is 3. So that's 10 to the 3rd, and then all we need is a square root of 9.17, which is going to be slightly bigger than 3, right? 3 squared is 9, so like 3.1 or something. So take the square root of that. I get 3.028, not even 3.1. Let's say 3.03. So that's 3.03 times 10 to the 3rd. We could write that as 3,000, right? We don't need to have this scientific notation when it's something that small. So that's about 3030, and everything is the right units. So it's speed, so that's how many meters per second. 3,030 meters per second, or we could say that many kilometers per second, which would be a perfectly good way to write it, maybe even better. 3.03 kilometers per second, or 3.03 times 10 to the 3rd meters per second. I guess I can't say kilometers per second there unless I take out the 10 to the 3rd. So, okay, so don't forget units. Meters per 3,030 meters per second, or 3 kilometers per second. On the Earth, you have to go about 8 kilometers per second. So it's a lot easier to orbit Mercury. It's smaller. Don't have to go as fast. Gravity doesn't pull as hard. All right. That's the first page. Hopefully you guys were able to get all these on your own. Then, next problem is the escape velocity of Mercury. All we got to do is multiply the last one by square root of 2. So V escape is equal to the root 2 times the orbital speed. Orbital speed, which is root 2 times, we just figured out, was 3030. So multiply that by square root of 2. And I get about 4.28, or 4280 meters per second, or 4.280 kilometers per second. And then you go that fast, and you're gone. Anywhere in between the two, and you're going in ellipse, and you go more and more elliptical until finally, like, no, you're out of there, and you escape, and you never go back to Mercury. Okay, how long would it take to orbit Mercury just above its surface? So now we need to know the period, which is typically written in big T. There's lots of ways we can figure this out. So let's see. We know that if you're going in a circle, which we're assuming, your velocity is the circumference of the circle divided by the time it takes for a circle. And we know the velocity, we just figured that out. We're not the escape velocity, but the orbital velocity, we're orbiting it. So we just switch the T and the V. So the period is 2 pi r divided by the velocity, and now we just plug in the numbers. 2 pi times the radius, which we said was 2.4 times 10 to the 6 meters, divided by the velocity we figured out was 3030 meters per second. And we plug all this stuff in. So 2 times pi times 2.4 divided by 3030. And then we multiply. Okay, so I'm just going to write this way so that I get 0.004976. 0.004, it's pretty close to 0.005. 0.00497, the 7 rounds up to 9, so that's about 0.005. I'm going to round off to that much, which is pretty close. And then times 10 to the 6, which means you move the decimal place over 6 places. So we go 1, 2, 3 is 5, 4, 5, 6. So that'd be about 5,000. And that'd be seconds, right? Everything's normally in seconds. And I want to know minutes because 5,000 seconds to our brains, like can't wrap my head around that. What's 5,000 seconds? So you take 5,000 seconds, divide it by 60, and about 83 minutes. So that's about 83.3, about 83 minutes. So about a little under an hour and a half to orbit Mercury, just above the surface. Okay, which is pretty close to what it is for Earth too. Earth you got to go faster, but you got further to go, and it ends up being a little pretty close to the same thing. Okay, what is g in meters per second 3 Earth radii above Earth's surface? Okay, let's draw a picture here. We're going to say it's 10 at the surface. Okay, so if you did 9.8, slightly different. So at the surface, we know it's 10. If we go 1 Earth radii above, twice the distance, because gravity goes as 1 over r squared. So twice the distance is 1 over 2r squared, right? Which is 1/4 of 1 over r squared. So twice the distance, it's 1/4 what it was. 3 times the distance, another distance above is 1/9. Another distance above is 1/16. 3 times further, 3 squared, 4 squared. We are 3 above. So here's 1 above, 2 above, 3 above. So we're all the way at 1/16. And I find it really helpful to draw this picture. It's kind of hard to wrap your brain around because you're already 1 above when you're on the Earth's surface. And then you go another one, another one, another one. So it's 1/16 of 10. So it's 1/16 of 10 meters per second squared, which so you go 10 divided by 16, or you could go 9.8 if you want to be more precise. I get it's about 0.625 meters per second squared. Okay, so if you go that far above it, you're not going to start falling very fast towards the Earth. Okay, Kepler's 3 laws. These are in the book. They're really famous. We talk about them in astronomy. You should know what they are. Kepler, just by looking at the planets, he didn't do any math. Well, actually, he did a lot of math to figure this out. Newton figured out all of Kepler's laws with F equals ma and with F equals g m1 m2 over r squared. All he needed are those 2 formulas, and had to invent calculus for the whole elliptical part to figure out Kepler's 3 laws. But Kepler got them by looking at the planets, by looking at actually Tycho Brahe looked at the planets and got really good data that Kepler did a lot of math with. And so what he figured out was that the planets, and it's all about planets, that's what he looked at. The planets orbit in ellipses. They have elliptical orbits. And the sun is at one focus of the ellipse. The other focus, there's this empty point in space. So sun is at one focus. And an ellipse looks like this, and there's 2 focus points. In astronomy, we mess around a lot with ellipses. And the sun's here, nothing's there. It's just a mathematical point in space. Okay, his second law says that the planets sweep out equal areas in equal times. So the planets, and again, you should look in the book, just get a better understanding of that, sweep out equal areas in equal times. And what that means is if you're going in your ellipse, so if it takes 1 month to go from here to here, it takes 1 month. This is the area that you sweep out. That's what they mean by sweeping out. From the sun, the thing you're orbiting, from here to here. And it's kind of an awkward area, right, because it's curved on this side. If that takes 1 month, then over here, the other side is the same area in a month. So this is 1 month. And notice you go a smaller distance because this area has to be the same. Since it's long and skinny, this is smaller. So in 1 month you go really far here and really short here, which means you go faster when you're close to the thing you're orbiting, and you go slower when you're far away. So when we're close to the sun around January 4th, we're closest, we are going fastest, and around July 4th, we're going slowest in our orbit around the sun. Our orbit's practically a circle, doesn't matter that much, but in a very elliptical orbit, it makes a huge difference. Okay, this again, he got that just by looking at data, which is pretty amazing in the 1500s, or is it 1600s? Way back then. And then finally, he figured out the relationship that the period squared is proportional. And this is a proportional symbol, like an infinity symbol, but you don't close. It's proportional to the radius cubed. And if you use years and radius of the Earth as a unit, then it's equals. In Earth years, period squared is proportional to r cubed. We derived that. I derived that one in the videos. That's this formula right here that Newton derived. Newton derived just by doing math, by doing simple math. From his formula is that t squared is proportional to r cubed, and the proportionality constant is this 4 pi squared over gm, or over root gm. This is a square root of gm there. It's always hard to tell. So Newton figured this out by basic principles, and Kepler just figured out by looking at the planets. And so a huge success of Newton's was deriving from basic principles, from basic mathematics laws that Kepler figured out by looking at the planets, by looking at planetary data. Huge accomplishment. Pretty amazing. All right. If the Earth were 5 times more massive, so we start off with G and the Earth. If it were 5 times more massive, it'd be 5 times bigger. G would be 5 times bigger. But 3 times greater radius would make it 1 over 3 squared times smaller. Okay, bigger you are, it's like you're above the surface of the Earth. It's like you're way out here. So if you make the planet bigger, again, you can't tell the difference. If the planet is inside your circumference, it might as well be all the planet at the very center, or a huge planet and you're standing on it. Gravity is the same because it's a sphere. Circular things, it's symmetrical, whether it's all in the middle or a big thing, doesn't matter. So bigger by 5, smaller by 3 squared. So that would be 5/9. So if we use 10, it'd be times 5 divided by 9. So gravity would be smaller because you're further away. So that's what, 50 divided by 9? And I get that that's about 5.55 or something. So let's say 5.6. But G is a little bit smaller than 10. So let's say 5.5. 5.5 meters per second squared. Okay, so just it should make sense. Oh, 5 times bigger, 5 times more massive. Just remember, distance goes by squared. If it was 3 times smaller, it'd be 9 times greater because it was smaller. Then it'd be really strong gravity. Okay, bottom of a 1,000-mile deep hole in the Earth. Okay, the Earth is 4,000 miles. As you go down, it's as if you're standing on a planet that's smaller. Okay, so it's all the mass above you. Here the mass, let's say you're standing here. Above your head, the mass is pulling you up. Below your head is pulling you down. You're further away from the stuff pulling you down. But there's more of it, in a sense. There's this whole part here. The stuff pulling you up, you're closer to. And then this stuff is pulling you sideways. It cancels. So it's just as if your gravity is, however fraction you're further down, that much weaker. If you're halfway down, gravity is only half as big. It's like you're standing on a planet that's half as big. Assuming the density. We're assuming the density is the same everywhere. It's actually not. The density in the center is greater. So actually it probably wouldn't quite work that way, but we're going to ignore that. So if you're 1,000 miles down, you're 1/4 of the way down, gravity is 1/4 weaker. Or it's only 3/4 as much. Okay, so you could take off 1/4 or go 3/4 as much. But, so basically gravity starts off at 10, goes to 0 in the center, and it goes down nice and linearly. So 1/4 less than 10, that's easy math, it'd be 7.5 meters per second squared. Again, using 10. So it just goes linearly from 10 to 0. You're halfway down, it's 5. You're 3/4 of the way down, you're 3,000 miles deep, it's about 2.5. All right. Okay, so this one we get to use Kepler's third law, which means the period squared is proportional to radius cubed. So she is exactly twice as far away from the sun as the Earth. So R is 2 AUs, and the AU is an astronomical unit, an Earth-Sun distance. So it's twice as far. So now we want to know how long it takes. So we can use t squared equals r cubed as long as we use Earth units. And our answer will be in years. So we are using Earth units. So for the Earth, we have 1 equals 1. 1 squared equals 1 cubed. So 1 equals 1. Here we have t squared is equal to 2 cubed. So the t is obviously going to have to be bigger. So that's of course equal to 8. So t squared is equal to 2 times 2 times 2, which is 8. So t is equal to the square root of 8. Plug that in my calculator. 8 square root. I get about 2.83. So 2.83, and that would be Earth years. If we do everything in Earth years, we get answers in Earth years. So if there was a planet twice as far from the Earth as the Sun, it would take 2.83 years to go around the Sun. A little bit more than 2 years because it's the radius cubed. The radius matters more, so it goes up faster. So small radius, small difference in radius makes a bigger difference in time. And that's because you got further to go. If you're in a bigger circle, you're not only going slower, your orbital velocity is slower, but you also have further to go, and it ends up being this t squared equals r cubed thing. We also could have used Newton's version with all the math in it. We could have used this formula here. So we could have said, okay, t squared is 4 pi squared r cubed, 4 pi squared r cubed square root of gm, and plugged in all those numbers, and we would have gotten seconds, and we can solve for t, take the square root of all this stuff, and we would have gotten the same thing. So don't bother doing that. This is a lot easier. But we could have done it from basic principles, and we would have gotten the same thing. Okay, that's it. So not so hard. The trickiest part's dealing with big numbers, so just be really careful in your calculator. Hope all that makes sense, and that you'll be ready for the test.